Yeah, so in the video, I basically tell you how to solve every problem, almost every problem, okay? And again, I'm kind of giving away the solutions because, as I said in the email, I know some people are still not gonna watch the video. They're not, they're just gonna leave the assignment till the very end, right? Till the last day, and then do it then, or ask someone else how to do it. Yeah, so make sure you watch that video, which is gonna serve as a study guide for the test. Okay, so this quiz is more like a study guide. I go over every problem. I tell you how to do it. You do it, you do that, you gotta do the assignment and get a grade. It's like a free grade. But 20 something points, 28 points. So it's up to you. Okay, that's that. And then the quiz is due what, tomorrow night? Yep. So we are gonna cover section 11.5, which is alternating series. Finally, we're going to be looking at series that are not always positive term. Let me just get rid of the camera because it's still staying down. Yeah. Is this? Yes, this section is also on the exam. Exam will be on 11.1 through 11.6. Okay. Yeah, so far the series that you guys been dealing with are positive term series, or eventually positive term, meaning that at some point they become, every term becomes positive. Okay, and an alternating series, of course, the name kind of explains itself. It is a series whose terms change sign. We haven't yet showed you how to approach an alternating series. Ari, I already answered that question. I don't know why you're asking that again. Yes, so what is an alternating series? Let me define it for you. Okay, so we mathematically write the form of this series. It is defined by the summation of, I'm gonna call the nth term u sub n, where n goes from 1 to infinity. So instead of using a sub n, we use u sub n. U sub n is the representation of an alternating sequence. Okay, which can be written as -1 to the n minus 1 times some a sub n. Okay, so if I expand this, when n is equal to 1, you get -1 to the power of 0, which is positive. You get positive a1. Next term will be -1 to the power of 1. That would be a negative a2, and then plus a1, plus, a3, minus a4, and so on. Okay, yeah. So the way I wrote down the form of an alternating series is that the first term is positive. It doesn't have to be. Some alternating series have a negative first term. Okay, so this could be in the form and from 1 to infinity, -1 to the power of n times a sub n, which starts with -a1. Okay, so again, some alternating series have a negative first term and some have a positive first term. But but I refer to the nth term of an alternating series as u sub n. Okay, so you see u sub n, it means that you have an alternating sequence. Okay, you have a -1 to the n or n minus 1 times some sequence. For example, we have the alternating harmonic series. Okay, -1 to the n minus 1 times 1 over n. You expand this, plug n equal to 1, you get -1 to the 0. That gives you -1. Second term will be a negative. So, sorry, first term is positive, +1 minus 1/2 plus 1/3 minus 1/4, and so on. Okay? Yeah. It turns out, I believe, if I recall correctly, this series is convergent. Okay? Well, we know that the harmonic series, the one without, of course, the -1 to the n minus 1, when all terms are positive, is divergent. Remember? If I make all these positive, then we get a divergent series. And it's barely divergent. Barely. It's on the verge of being divergent convergent. And we discussed why, because it is a p series with p equal to 1. And if we know that if p is 1 or less, the p series is divergent. If it's more than 1, it's convergent. So if you have, yeah, let me write that down. We know the harmonic series diverges. Okay, and again, as I said, it is barely divergent. It's on the verge, on the threshold of being divergent convergent. Let me expand this a little bit. So all terms are positive. So again, it's a p series with p equal to 1. 1 is on the borderline. 1 is on the borderline of the p series becoming convergent. Okay, so this again barely diverges. Now imagine you make some of the term, like half of the terms negative. What do you think is going to happen? Divergent or convergent? What do you think?
Convergent.
Convergent.
Yes, you are subtracting some terms away. Half of the terms are being added, half are being subtracted. So you have some positive, some negatives. It's going to become convergent. This thing converges. So the harmonic series itself diverges. Okay, and again, it diverges very slowly. Remember that problem we did? If you have a supercomputer that you run for 14 billion years, this series barely gets to, like, what was it, 60, something like that. It doesn't grow much. So it diverges very slowly. So it is reasonable to say that the alternating form of it converges. Okay, again, that's because we have in a way positive negative terms canceling out. We have addition and subtraction. And it turns out, I believe the value of this series, I think it's ln of 2. Yep, this is natural log of 2. And we're gonna see why later on, but it's a convergent series because if you think about it, for the partial sums, it's all about partial sums. What happens is that, well, we start with 1. Okay, so imagine this line is the number line, and you're plugging the partial sums here. Okay, so you are initially at 1, and then you take half of a step backwards. 1 minus 1/2. You go, so say this is 0, you go backwards by half. And then you go forward by 1/3. Okay, backwards by 1/4. Forwards by 1/5. You get somewhere here. It's just that you just keep going forward, backward until you stop. Okay, somewhere in between 0 and 1. Yeah, let me plug here. I'll just plug the partial sums for you. So you get an idea of how alternating series works. This is the n-axis. And again, I am going to plug in the partial sums. S sub n is a partial sum. Partial sum is you adding the first n terms. Okay, so for when n is equal to 1, when n is equal to 1, you get S sub 1, which is basically just 1. Okay, S sub 1 is the first term of the series. It is 1. Let's say 1 is right. Where would 1 be? Let me see. 1, 2, 3, 4, 5, 6, 7, 8. Let's say 1 is here. So S1 is plotted is right there. Okay, this is S1. Okay, S1 is 1. And then S2 is the sum of the first 2 terms. It'll be 1 minus 1/2. 1 minus 1/2 means that you're going to go down by half. Okay, so when n is equal to 2, we go down by half. Half is right here. We get to half. That is S2. Okay, so S1, you go up by 1. I went up by 1. S2, come back down by half. Did I count that correctly? Here, let me see. S2 goes over here. Yeah. So S2 go back down by half. Okay, and then S3 go back up by third. Because S3 is 1 minus 1/2 plus 1/3. From to the previous step, you add 1/3. So just go third of the way up, you get to S3. Okay, we went up. And then S4, it's 1 minus half plus 1/3. Go down by a fourth, minus 1/4. Okay, so from where we are, from S3, we're just going to go down a fourth away. We're going to go down by 1/4. And what happens is that your partial sums are going to like fluctuate like that. They fluctuate like that, and then at some point, it's just going to stop. Okay, you get a convergent series. Okay, so the picture of partial sums shows you what's happening in terms of convergence. Is this related to squeeze theorem? No. It seems like, it looks like it's squeezing, but it's not. Squeeze theorem is when a function is between 2 other functions. But what's happening here is that the partial sums are doing that. They're just fluctuating because you have positive, negative, positive, negative, positive, negative, positive, negative, and then at some point it just becomes convergent. It looks like it's squeezing. Yes, but it has nothing to do with the squeeze theorem. Okay. So what are we learning here? We are learning that it is easy for an alternating series to converge. It is easy because you're adding, you're subtracting. You add, you subtract. And when you take some negatives from positives, you're highly likely to end up with a finite value. Okay, so an alternating series is highly likely to be convergent. Okay, more likely than a positive term series. And well, how do we know if an alternating series converges? Here is the theorem, which is called the alternating series theorem, or the alternating series test. All right, and it says that if you have a alternating series, -1 to the n or -1 to the n minus 1, who cares which form you have? So this is a1 minus a2 plus a3 and so on. Okay, the theorem says that this thing converges if two requirements are met, if two things are true. Number one, well, if you think about it, the sequence has to go to 0. Okay, this thing has to get, these numbers have to get smaller and smaller. They have to go to 0, right? So the limit of a sub n should equal to 0. Imagine, guys, imagine if the limit doesn't go to 0. Okay, here, I'll discuss what happens if the limit doesn't go to 0. So these are the reasons. Like, assume limit as n goes to infinity of a sub n is equal to a number L, and L is not 0. Okay, so L could be anything but 0. L could be 1, L could be 10, L could be infinity. It could be anything. So what happens is when you expand the series, you get a1 minus a2 plus a3 minus a4 plus. When you do this long enough, what's going to happen is that you are eventually going to get L's, minus L plus L minus L plus L, and so on. Okay, well, negative L plus L minus L plus L is not convergent. Remember, guys, we discussed this in section 11. When was it? Section 11.2. I can go back and show you. Hang on one second. Yeah, section 11.2. Well, if you just think about it, if you add if you add negative L plus L, the partial sum is not going to have a limit. Okay, just think about this for a second. The partial sums will not have a limit because you're either going to get, if you add negative L plus L, you will get 0, okay? Or you get what? Let me see here. Yeah, adding a negative L to L minus L plus L. Okay, this is not going to have a it's not going to have a deterministic sum, because you can group the terms by doing by adding the positives and negatives. Or look, S1 will be L or negative L. Here, look at the partial sums. Look at the partial sum. Just focus on this. Focusing on this only. Okay? Forget the rest. So again, the sequence eventually becomes L. So if you look at the partial sums for this, first term will be negative L. Second term, S2, the second partial sum will be negative L plus L, which is 0. Third partial sum will be negative L plus L minus L, which is negative L. S sub 4 will be negative L plus L minus L plus L, which is 0. So these partial sums, they're going to fluctuate between negative L and 0. They're either negative L or 0. So there will be no limit because we don't get the same value every time. Okay. And the series will be divergent. Limit of the partial sum does not exist. All right. So we want A sub n to go to 0. All right, so that's one requirement. The second requirement says that A sub n should decrease. All right, and that is the same as saying A sub n should be greater or equal than A sub n plus 1. This means that the sequence should be non-decreasing or non-increasing, sorry, non-increasing. Just think about it. If a term is larger than the next term, then the sequence is a decreasing sequence. With the equality, it means non-increasing. So this should be true for all n or eventually. Okay, which means that A sub n must be non-increasing. Okay, decreasing or sometimes the same. Because just think about it. If the sequence is increasing, then this is just going to totally diverge. Okay, so S1 will be right there. S2 is going to be larger, so you're going to be going down here. S3 will be larger than that, so it's going to do, look at this, it's going to do this. Okay, it's just going to blow up. All right, so we need A sub n to be decreasing. All right, well, again, let's show you why the AST is true. Any questions before I draw the picture? Okay, so let me show you. Do you need absolute value? What do you mean? Do you need absolute value? No, we don't. We don't need absolute value.
Well, doesn't it go from positive to negative? So doesn't it?
Yes, it does. If A sub n was increasing,
Yeah.
yes, it would. Yeah, but who cares? It's an alternating series. Okay, but let me show you why the ASC is true. So this is in a way proof by picture. And again, we are gonna assume A sub n is non-increasing and the limit of A sub n is equal to 0. So again, so this is just like the alternating harmonic series that we discussed. And we are looking at this alternating series, -1 to infinity, -1 to the n minus 1 times A sub n. Okay, and again, we'll be looking at partial sums. Okay, partial sums. So here, if I expand this, the expansion is A1 minus A2 plus A3 minus A4, and so on. All right, so here S1, the first partial sum is just the same thing as A1. Okay, so when n is equal to 1, you go up by A1. I'm going to go up. This distance is A1. Okay, and S1 would be right here. Okay, now S sub 2 is equal to A1 minus A2. Yeah, it's the sum of the first two terms. Okay, we are gonna go down from wherever we are from S1. Here we're gonna go down by A2. Now, the sequence is non-increasing. It is non-increasing. So here A2 is gonna be less or equal than A1, meaning that when you go down by A2, you're not gonna exceed the horizontal axis. Okay, so since A2 is less than A1, going down by A2. So from here we go down by A2, and again, since A2 is smaller, we're gonna end up, say, somewhere here. That will be S2. So again, if A2 was larger than A1, then S2 would be somewhere down here. The partial sum would become negative. And no, we don't need absolute values. The series is this. Why would you absolute value it? You absolute value the terms, you're changing the series totally. And that's not what you should do. S sub 3 is going to be A1 minus A2, okay, plus A3. Okay, so if you think about it, A1 minus A2 is the same as S2. And to S2, you're going to be adding A3. Okay, so from wherever we are at S2, we're just going to go up. We are adding by A3. We'll go up by that amount, by A3. All right, now again, A3 is not going to exceed the previous A. Therefore, we are not, when you go up, we are not going to go up beyond this value. Okay, so from S2, go up by A2. This is the location for S3. Again, we saw this in the alternating harmonic series. All right, so likewise, S sub 4 is going down from S3 by A4. Okay, go down, subtract A4, and that will put you at S4. All right, so again, you see some sort of a finite n behavior, okay? This is just gonna the magnitude is just going to keep shrinking. And the series will converge somewhere around here. Okay, so there will be a value L there will be a value L which the partial sum is going to approach. All right, so if I keep plotting, this will happen. Going to converge to L. All right. Does that make sense, guys?
Yeah.
Okay. Good. All right. Well, let's do an example. So again, it
Wait,
is.
Professor.
Yeah.
On the quiz video, you said to do the absolute convergence test first. Does that only apply to the alternating series test?
Yes, it does. We'll discuss that. Yes. We'll get to absolute convergence in a second. And please remind me, okay? Remind me to tell you what to do with those problems. All right. So let's do an example and then we'll talk about absolute convergence. Okay. Here we have an alternating series. Let's say n goes from 1 to infinity. We have -1 to the power of n. It could be n minus 1. It doesn't matter. It's still alternating. And here a sub n is, let's say, 2n over 4n squared minus 3. Okay, so again, here a sub n is that. Again, guys, as we said, it is easier for an alternating series to converge. Okay, so if you have a series, it is highly likely to converge as long as it is alternating. All right, so you're gonna show two things. This test is highly mechanical. You don't have to you don't have to do a comparison or anything like that. You just have to check the two requirements. Number one, check the limit of a sub n. Okay, that would be the limit of 2n over 4n squared minus 3. All right, so here we have a rational sequence because it is a fraction. The denominator has a larger power, so the denominator increases faster than the numerator. Therefore, you're going to get 0 for this limit. All right, you can use L'Hopital rule if you want. But again, if the degree of the bottom is higher than the degree of the top, the limit is 0. Okay, so this checks out. All right. Second, you need to check that a sub n is a non-increasing or just a decreasing sequence. A sequence is a function. You just want to show the function is decreasing. The best way to do that, the easiest way to do that, the way that requires no thinking is just by taking the derivative. Show that the derivative is negative. Okay, it could be negative for all n, or it could be negative eventually. It doesn't really matter. Okay, so to see if a sub n is decreased, let's just go with decreasing. Or again, eventually decreasing. I'm gonna let f of x equal to 2x over 4x squared minus 3. Why did I do that? Well, we are used to taking the derivative of a function whose variable is x. Okay, you can keep n if you want. It's totally fine. You can call it f of n, take the derivative with respect to n, or you can call it f of x, take the derivative with respect to x, x, and that's just a dummy variable. Nobody cares. And here x is greater or equal than 1. Well, why is that? Because here n starts at 1. All right, so differentiate now. Again, there are multiple ways that you can show a sequence is decreasing. Derivative is one way. You can also directly show, if you want, you can directly show that a sub n is more or equal than a sub n plus 1. There's a lot of algebra involved. Okay, you could do that. You can show this inequality is true. Or you can even look at the ratio of a sub n plus 1 to a sub n. If this ratio is less than 1, the sequence is decreasing. Okay, there are 3 ways that you can show a sequence is decreasing. You do the ratio thing if you're dealing with factorials or factors, but because for factorials, we definitely can't take derivative. But this is just a rational, again, this is a rational function. Derivative works out nicely. We're gonna square the bottom, quotient rule. Okay, take the derivative of top, the derivative of 2x is 2. We multiply that by the bottom. Minus top, which is 2x, times the derivative of bottom. The derivative of 4x squared is 8x. The derivative of 3 is 0, so just 8x. Okay, and that is equal to, all right, so on top we have 8x squared minus 6 minus, what is that? 2x times 8x is 16x squared over 4x squared minus 3, the whole thing squared. All right, so top gives us 8x squared minus 16x squared. That's a negative 8x squared. Then we have this minus 6. You can take out the negative and get 8x squared plus 6 over whatever the bottom is. All right, so if you think about it, guys, just think about it. This function, this expression is always negative. I factor out the negative. This whole thing is always negative. And that's because the top is the sum of 2 perfect squares. X squared, that is never negative. X squared is non-negative. Add 6 to it. The whole thing on the top is always positive. The denominator has a square, so that whole thing is always positive. You have a positive over positive with a negative in front. That makes the whole thing less than 0. Okay, and that is going to be true for all x. For all x. Okay, therefore, here a sub n decreases for all n greater or equal than 1. It's not even eventually decreasing, it's always decreasing. And that's it. We check the second requirement. So the series is convergent. Converges, please make a reference to the test by alternating series test. That's what AST stands for. All right. Questions on this problem, guys?
If we find that it's decreasing, can we also just say the denominator will always be greater than the numerator?
No, that's not always true. Just because the denominator is larger than numerator, it doesn't mean that the sequence is decreasing always.
Okay.
Yeah, and try to think why. So that means the sequence goes to 0, but it doesn't mean it's a decreasing sequence. Okay, because let me see why. Yeah, because if denominator goes to 0, again, that means the sequence is going to 0. If the denominator is bigger than the numerator, again, that means the sequence goes to 0. A sequence goes to 0 by being increasing. Okay, here is such sequence. The sequence is increasing and it's going to 0. So you see what's going on? Just because a sequence goes to 0, it doesn't mean it is decreasing. You could have a increasing sequence that goes to 0.
So Professor,
Uh-huh.
for AST for either steps, if they turn out to be not negative or not 0, does that mean that the series is then divergent, or is it inconclusive?
Divergent.
Divergent. Okay.
Divergent for sure. Yeah. Let me see here. I can do more problems. All right, so let's say we have this series. -1 to the n times, let's say 2n over n plus 1. Okay, it's an alternating series. So we run the AST to see if it converges. Number 1, take the limit. Okay, your a sub n, make sure you identify a sub n is the part without the -1 to the n or n minus 1. It's 2n over n plus 1. Take the limit of that. Okay, this limit is 2. Because again, the degree of top is 1, degree of bottom is 1. So you just take the dominant term on top, which is 2n over the dominant term on the bottom, 2n over n, that gives you 2 as the limit. Okay, and that is not equal to 0. Okay, so the series diverges and we are done. All right, and you don't need to check the second requirement. So again, what this says is that if you expand the series, write down the terms. If you run the series long enough, you're gonna end up with +2 minus 2 plus 2 minus 2 plus 2. Okay, 2, yeah, and this series here is not gonna be convergent because the partial sums don't have a limit. The partial sum is either 0 or 2, or 0 or 2 if you add the partial sum, 0, 2, 0, 2, 0, 2, or if you group it differently, it'll be 0, -2, 0, -2. Partial sums will not have a limit. Okay.
So it's like the same thing with cosine of pi n.
Yes, yeah,
Okay.
because it's alternating. All right, another one. Let's say we do this example. This is very obvious, guys. It's so obvious. Let's say we do -1 to the n, and then let's just say that the sequence is n. Isn't this obvious? It is obvious. So if you, of course, a sub n doesn't go to 0, okay? But if you look at n, let me see if I have a better example here than that. Yeah, if you look at n, n is not decreasing. The limit is, first of all, not 0. The limit is infinity. So we are done with that. But if you look at n, n is an increasing sequence. It's an increasing sequence. It goes to infinity. So the partial sums get bigger. Okay, and definitely we don't expect any convergence. Does that make sense, guys? The limit as n goes to infinity of a sub n but yeah, so that's equal to infinity. That is not equal to 0. So we are done with that. And also this a sub n equal to n is increasing. Okay, so if it's increasing, the partial sums are going to diverge. Okay, it's just going to go to infinity. Anyway, this is not a great example. Not a good example. It's so obvious. But we're going to do more. I promise you, we'll do more when I cover absolute convergence. Let's talk about that and get that out of the way. Yeah, so what does absolute convergence mean? What does that mean? Imagine we have an alternating series, okay? You have an alternating series and someone said, should we absolute value the terms? Let's say you have an alternating series and you totally ignore the fact that it alternates. Let's say you make all the terms positive, okay? And when you make all the terms positive, it converges. Then we say the series is absolutely convergent. Okay, so that is just a definition. It's not a theorem. Yeah, we say that the sum u sub n, again, u sub n here stands for alternating or not always positive. We say it converges absolutely. If the sum of the positive of the terms, the sum of the absolute value of the terms converges. That's what absolute convergence means, okay? And again, this is something we do on a series that alternates, okay? If a series is positive term, if you don't have that -1 to the n or n minus 1, and it converges, then it is already absolute convergent. Okay, so absolute convergence is something you do on an alternating series. Okay, not a positive term series. ABS here stands for absolute. CONV means convergence, but we are interested in absolute convergence of an alternating series. Okay, a positive term series that is convergent. If you have an alternating, if you have a regular positive term series that converges, then we know it's absolutely convergent because all terms are already positive. Okay. Yeah. Example. Again, negative n or n minus 1 of, let's say, 1 over n squared. Okay. Yeah. So what you do again, u sub n, guys, u sub n is this whole thing. Okay, so absolute value u sub n to the absolute value of every term And what the absolute value does is that it drops the -1 to the n minus 1. And you just get the summation of 1 over n squared. Okay? Taking absolute value makes every term positive, and you get the sum of 1 over n squared, which is a p series with p more than 2. It is convergent. Convergent because it is a p series with p more than 1. Okay, so we say that the original series is absolutely convergent.
So the first example that we did where it was the alternating series of 1 over n, that would be conditionally convergent.
Yeah, I haven't yet defined conditional convergence, but yes. Okay, taking positive terms convergent, then the series is absolutely convergent. All right. Yeah. And here is a theorem about absolute convergence, which is highly useful. Highly useful. Because sometimes when we check an alternating series, by doing the AST requires two things. You need to take the limit. You need to see if the sequence is decreasing. Sometimes running the AST could be difficult, okay? Because you have to take limit, you have to take derivative. Trust me, for some series, taking the limit is not easy. Taking the derivative is not easy. Showing the sequence is decreasing is not easy. Okay, so let's say you have an alternating series and you check for absolute convergence and say it converges absolutely, then guys, you listen hopefully, then you don't need to check the AST. If a series, if an alternating series converges absolutely, then it is convergent. You don't need to check AST. Okay, this is a very powerful theorem. A theorem for absolute convergence. We say if wait, why is not changing? Okay, there we go. If an alternating series, again, I call that U sub n, if it converges absolutely, okay, then the series is convergent. All right, so here we need no need for AST, alternating series test. All right, it's really cool. Just think about it, guys. Think about this theorem. If you make all the terms positive and the series ends up being convergent, then it is guaranteed for the series to converge. Because if all positive terms added, you get finite, then for the alternating series, we have addition, subtraction, that should also converge, okay? If all positive terms converge, then positive negatives also gotta converge. For example, yeah, this is what we just did. We just said that this thing converges absolutely. We did that in the last example. Okay, then therefore I should say, therefore it is convergent. All right, I don't need to check AST. I can check AST. You can check the alternating series test if you want. It is going to end up telling you that it's convergent. Okay. Does this make sense, guys?
Yep.
Okay, cool. Yeah. So what if we have a series that converges, that does not converge absolutely? We have some series, like the alternating harmonic series. If you check for absolute convergence, it is not gonna it's not gonna check. Here, I'll show you an example before I write the definition. Yeah, this is the harmonic series, alternating harmonic series. And we checked that this thing is convergent. We checked it already, but did we check it? But we discussed it. Yeah, we discussed that this thing is convergent. But if you check for absolute convergence, so just do absolute value of the terms. Okay, you get the harmonic series. It is divergent. Because here is harmonic. Okay, so this series is not absolutely convergent. All right, yeah. But if it doesn't absolutely converge, it doesn't mean it is going to diverge. It's just not absolutely convergent. If you check AST, okay, run the alternating series test on the series. Okay, so here are a sub n is equal to 1 over n. Check the two requirements, limit as n goes to infinity of 1 over n, that is equal to 0. That checks. Okay, also, we want to show the sequence is decreasing. Again, you can do the derivative test if you want, or you can just directly show it's decreasing. Let's just do the derivative test here. F prime of x is negative 1 over x squared. That is less than 0 for all x. Okay, therefore, this is x greater or equal than 1. Therefore, a sub n is decreasing. All right, so AST says that the series is convergent. And it's by AST. So what do we got? We got a series that doesn't converge absolutely. It's not absolutely convergent, but by AST, it is convergent. In this scenario, we say that the series is conditionally convergent. We have absolute convergence. We have conditional convergence. All right. Yeah. So the definition of conditional convergence is that if a series is not absolutely convergent, but it is convergent by AST, then it is conditionally convergent.
So, Professor, just quickly, so is it strategic to do to check for absolute convergence first and then see if it converges or not, or is it just a matter of like us checking for AST first or not? Like, does
Yeah,
that-
good point. Let's, yeah, very good. Let's talk about that. So if you have a series, what would you do? What would I do? If you have a series, check for absolute convergence first, because
Mhm.
it's easy. If the series is absolutely convergent, then you're done. It is convergent and you don't need to check AST. You don't need to take the derivative. You don't need to find the limit. It takes out the need for doing all of that. Okay? Yeah. Let me write all of that down for you over here. So let's say we have a series, call it U sub n, the summation of U sub n. All right. So what you do is check for absolute convergence. Okay, by looking at the sum of the positive terms. Okay, sum of the absolute value of the terms. Okay, so if this thing converges, yeah, let me hold on. Let me fix this, guys. Let me fix this for you. Yeah, so that's what I do. I check for absolute convergence. Okay, yeah. So you're looking at the sum of the positive terms. Okay, if you decide that the sum of positive terms is convergent, if it's convergent, then we are done. We say that this thing is convergent. Okay. It's absolutely convergent, then the series is convergent. We don't need to do any AST. You don't need to check the alternating series. Okay. If you check for absolute convergence, you look at the sum of the positive terms. Let's say it is divergent. Then you're gonna run the AST. Okay. So check for AST. All right, AST is going to tell you two things. It could tell you that the series is either convergent. If this happens, then we have conditional convergence. Okay, and if AST says divergent, then it's divergent. It's done. Okay. So again, you have a series. Look at the sum of the positive terms. If you get convergence, then you're done. The series is absolutely convergent. If it's not, then you check the AST. Okay. Just like what we did in the last problem, and we are over time actually. Yeah, so very quickly, here is our question. Alternating series, harmonic alternating series. I check for absolute convergence. I drop the -1 to the end, and I end up with a conclusion of divergence. Okay, so the series is not absolutely convergent. Now I go ahead and do AST. AST tells me that it is convergent. Therefore, the series is conditionally convergent. All right. Yeah, we'll come back tomorrow, do more problems, finish the section. So for the quiz, guys, for the quiz, you only need to check for conditional convergence and absolute convergence for series that alternate. If a series is already positive term series, then you just check regular convergence, divergence. Okay, so absolute convergence, conditional convergence, just do that on an alternating series, not on a positive term series. All right.
Thank you.
Are we able to do most of the homework?
Thank you, Professor.
Yes, you can do the homework now, all of it.
Professor,
Yeah.
mind if I run 2 really quick questions about the quiz through you?
Right now,
Yeah.
hold on. So